Now that we have some facility with the language of continuum mechanics, we can start to interrogate the ice flow problem, because ultimately glaciers behave like fluids. They are straining in response to an applied stress, but they're very viscous. They're slow to deform. And so if we want to understand the details of ice flow, we have to start to break apart what are the stresses that are driving the deformation of ice, and then what are the stresses that are resisting that deformation. If we can answer those two questions, we can learn a lot about how glaciers behave. Oops. So, here we are, the ice flow problem. I always like to start thinking about this problem by looking at a map of velocities in Antarctica. So this map on the right here, it's color-coded by how fast the ice is flowing. And what we see is that there are these complex networks of ice streams that are draining ice from the interior out to the ocean. But the pattern of these ice streams wouldn't be immediately apparent just by looking at the geometry of the glacier systems alone. There's a lot about the specific materials in specific locations that control the pattern of ice flow. So we're starting with the high-level understanding, the kind of physics framework for thinking about this problem, but there's a lot of unknowns about specifics in individual glaciers that we have to get right in order to predict their ice flow behavior. Ultimately, ice flow can occur by two processes. The first process is simply the deformation of ice itself. So if we imagine a glacier as a stack of boxes of ice, so this is vertical here, each of these boxes can deform, subject to the stresses that are being applied. It turns out that the stresses are higher at the base of glaciers than near the surface. We'll talk about why in a second. But that means that the boxes at the base of the glacier system are deforming rapidly. Imagine that we fix the position of the bottom of this box. Let's say we freeze it to the rock underneath. If that box is going to deform, and deform by a shear stress, which is one of the dominant stresses in glacier systems, we might expect that box to turn into a box that looks like this. Shearing, if the glacier is flowing from left to right. That carries with it all of the boxes that sit on top. But those boxes are also deforming. They're deforming a little bit less and a little bit less as we get closer to the surface. But each deforming box in our glacier is carrying with it all of the ice above. To the point where we may expect the deformation of the system to result in an ice column that looks like the one I've just drawn in black, where at the base of this glacier, you're not moving much at all. But up near the surface, the rate that you're moving is the integrated deformation from the bed all the way up. Turns out that is the case. So one of the ways ice flows is by a process that we often call internal deformation. And internal deformation, this total distance traveled, is really the integrated strain as a function of depth. You add up the deformation of all of those pieces of ice and you get to the total deformation at the top. The other way ice can flow is by a process we call basal sliding, where if this is our column of ice, this is the rock underneath, the whole column of ice can translate forward as it moves past the rock underneath. This can be accommodated either by fully decoupling the ice from the rock. Maybe you have a pressurized layer of water that separates them and the ice can simply move past the rock. Maybe whatever's underneath the glacier is deforming itself. You could have some unconsolidated material that also deforms in response to an applied stress, and as that rocky material deforms, it carries with it the ice above. So to think about ice flow, we need to think about how stresses result in both deformation and sliding. Let me write that down here. Basal sliding, we often call it. The first question we can ask ourselves is, what's the primary stress that drives glacier flow? Why are these boxes deforming? The primary driver is gravity. And so we call that the gravitational driving stress. There are two ways to kind of frame our thinking of the gravitational driving stress. It turns out the math for both of these problems results in essentially the same answer. We can think about, for example, ice sitting on an inclined bed. We'll call this slope. The slope of our glacier is alpha. But here's our ice sitting on that inclined bed. Alternatively, we could draw a glacier that has a flat bed and an inclined surface. In both of these cases, ice will flow from left to right because of gravity. I'm going to show you the math for the case on the left, and then we'll just think about the intuition for the case on the right. So let's think about the gravitational force acting on this glacier. The gravitational force is downward. We can resolve that force into a stress at the bed of this glacier. That stress has two components, a normal stress and a shear stress. If we think about the force due to gravity, to get to the force due to gravity, we have to think about the mass of the object being pulled down. The mass of that object is related to its density. If we're thinking about this as just a single column of ice with some fixed area, we might think about the mass as the density times the cross-sectional area times the ice thickness. Ultimately, the stress is per unit area, so we can get rid of that term right away because we're going from force to stress. That's the mass. To get to force, we need mass times acceleration, so we accelerate this, we multiply this by acceleration due to gravity. So if we want to get the total tension surface force applied at the bed of this glacier, we would take rho A hg, divide it by area, because stress is force per unit area, and we're left with rho hg. But remember, that has two components. One component that is perpendicular to the bed, and the component that drives flow, which is parallel to the bed. If we want to think about if this is our tension force from gravity, this is also alpha. If we want to know just this component of our stress, our shear stress at the base, then we can take our gravitational tension, which is here, times sine alpha. And what we end up with is a shear stress, x, actually we'll call this zx, acting on the z face in the x direction, is equal to rho g h sine alpha. This is our consistent term for the gravitational driving stress. If you look anywhere in this ice column at a depth of h, you choose your depth, you can figure out what the shear stress is acting at that depth to deform the ice. It's rho gh sine alpha. You don't need a bed to be sloping downward to get ice to flow. What you actually need to get ice to flow, to guarantee ice flows, in this case from left to right, is a surface that's tilted from left to right. If we think about why that's the case, we can go at two different cross sections of this glacier. Underneath the surface, the weight of the ice is acting to apply a pressure. The pressure here, just as in the previous case, is rho gh. If we look at this system at 2 points of constant elevation, the pressure is going to be higher on this face than the pressure on this face. The difference in that pressure depends on how much, if we define this as a change in x, how much the height changes over that change in x, dh dx. Turns out dh dx is also tangent of alpha, where alpha is the surface slope. And when we're dealing with really small surface slopes, tangent alpha, sine alpha, alpha, they all look quite similar. So that leads us to this general relationship. The driving stress is rho gh sine alpha. That stress, how does that stress lead the ice to deform? There are lots of different ways to think about the ultimate deformation and flow of ice. But it's important to remember that ice is a crystalline solid. And in fact, glacier ice is made up of many ice crystals. So if you've ever looked at a snowflake, you've seen that snowflakes are these beautiful six-sided things. They're six-sided things because when you look down if you look down on an ice crystal, they have a hexagonal structure. The hydrogen bonds in these H2O molecules lead to this nice hexagonal structure. This plot on the right is looking down what we call the c-axis of an ice crystal. This plot over here on the left is looking at the perpendicular image. We're looking across at the perpendicular side of the c-axis. And what you see is that the ice crystal is actually bound up in these tight planes. It turns out ice is really easy to shear along these planes. You can deform it by breaking bonds and reforming bonds by shearing along what we call the basal plane. The crystal stays a solid, but as you break a set of bonds and new ones form by a process that we call dislocation glide that leads to the evolving shape of these ice crystals, even though it stays a solid the whole time. So one of the ways that when we apply a stress, ice crystals deform is by the breaking of bonds across from these basal planes that leads to shearing. In addition, this here is a thin section of polycrystalline ice. Each of those little polygons you can see there is a separate ice crystal. You can have grains that slide past each other when you apply a stress. You can also cause H2O molecules to move around, to switch from one grain to another. That recrystallization process can also cause the ice to change shape. And so at the microcrystalline level, we can have crystals sliding past each other, we can have diffusion between crystals, we can also have the motion of dislocations within the crystal, all of which lead to deformation of the ice, evolution of its shape. Ultimately, what controls the rate at which ice deforms are these processes that resist the driving stress. Something that has to be true about these slow-acting systems like glaciers is that everywhere and always the stresses are in balance. So if there's a gravitational stress that is applying one stress to the system, there has to be some compensating stress that is equal and opposite. One of the equal and opposite stresses comes from the internal strength of ice itself. Remember, we said that ice behaves like a non-Newtonian fluid. Its strain, in order to strain it, there has to be an applied stress. That gravitational stress can be balanced by the internal shear stress within the fluid. Because the fluid has some strength, it wants to resist deforming. As you start to deform the system, just like friction, as it starts to move, you have this internal friction that eventually becomes equal and opposite to the driving stress. And so you'll have some associated strain rate that is balancing the driving stress. In the simplest framing of a glacier system, we say that the full driving stress is balanced by just a frictional stress applied by the bed. We call basal drag. This model, where we assume that's the only resistive stress in the system, we call the shallow ice approximation, where we have the driving stress is perfectly balanced by that internal viscous stresses and basal drag. That leads to a very simple model of ice flow that we call the shallow ice approximation. You'll see in this equation, I've actually framed this in kind of a generic way that's better to be a little bit more specific. Remember we said ice can deform in many different ways. It can deform, let's just do this in the two-dimensional case for a second. We have all of these different potential strain rates. Ice can stretch, ice can shear. The general rule is that the strain rate in one of these orientations, to be generic, I'm just going to call it ij, is equal to some, what we call a prefactor, it's a constant, times an I can say squared here, this is true for ice, times an effective stress squared. This term is some combination of all of our stresses. And we're not going to talk about the details of the math here, but that effective stress represents something about the average stress state of the system, times the stress of just the component of interest. My cat really wants to talk about ice flow. Here's Cinder. Hi Cinder, look at the camera. I'm going to put her away while we talk about ice flow. So, when we generalize the deformation of ice, what we say is that all of those mechanisms we talked about before, they kind of add up to this aggregate behavior, where any individual strain rate component is equal to the prefactor times the effective stress, which is some average stress state in all of the orientations, times just the stress in the orientation we care about. So, what is the prefactor? How do we think about the prefactor? The prefactor tells us how readily the material deforms for a given stress. Remember, in the most generic sense, we say strain rate equals A tau to the third. A prefactor that's larger means that at a given stress, it deforms more. A prefactor that's smaller says that at a given stress, it deforms less. This prefactor depends on things like temperature. When the temperature is high, the ice is more deformable. The dislocation glide process, grain boundary sliding, all of those processes happen more readily. So the higher the temperature, the higher the prefactor. It turns out this A also depends on things like the grain size and the crystal orientation with respect to the dominant stress direction. Because ice is really weak along those basal planes, it's really easy to deform if your shear stress, your driving stress, is resolved along those basal planes. Deforming ice in any other orientation is actually really, really hard to do. So, if you have ice in a favorable orientation, if it's warm, if its grain size promotes some of these mechanisms, then you lead to a high prefactor and ice deforms very quickly for a given stress. One last thing to consider, this introduces some real complexity to the ice flow problem, is that ice and the deformation of ice is something we can characterize really well in the lab. And we can come up with that constitutive relationship, which we call Glen's flow law, which I should have written down. I'm going to write that here. Glen's flow law. That's what says the strain rate equals A tau to the third. We have this nice rule that tells us how the resistive stresses will develop within the ice. But at the base of the ice column, we don't have as clear a picture of the physical processes that result in glacier sliding. It could be the case that glacier sliding and the stress that the bed applies on a sliding glacier, the resistive stress applied by the bed, it could be that that's a linear viscous process. That as we increase the stress, the sliding rate goes up linearly. There are some situations where we think that's the case. It could be the case that, like ice, it's some other nonlinear viscous process, where the strain rate and the stress are still related. And so ultimately the sliding rate will reach some value that frictional stress, that shear stress, equals the driving stress. It may also be the case that interface between ice and rock underneath behaves plastically, that it won't slide at all for some stresses, and the bed will just apply a resistive stress that balances the driving stress with no deformation. Or as you cross some threshold that we call the yield strength, then it just fails catastrophically, and you can slide as fast as the glacier system wants to slide. We're still doing a lot of work to tease apart, is glacier sliding governed by a linear viscous process, a power law process, a plastic process? That has significant implications for the dynamics of glaciers. So there's an area where there's still a lot of research going on, and one of the things that I try and do observationally is determine, can we figure out what the material is under the glacier, and can we use that to help us understand the likely physics governing glacier sliding? This is a lot. These are complex ideas. Hopefully this gives you some sense for the physics of ice flow.